just a little bit more to go. So I want to talk about osmosis. So osmosis is another colligative property. And osmosis is the effect by which you have two solutions separated by a semi-impermeable membrane. So what that semi-impermeable membrane means is typically ions can pass through it, or excuse me, typically water can pass through it. What do I have going on here? So basically it means it allows you to pass a solvent through or ions through in the limit that both solutions have the same concentration. Okay? So for example, in this picture right here, so you can see on this side there's seawater, 1.15 molar, really concentrated. If, let's say, on the other side of the semi-impermeable membrane, it was the exact same concentration, nothing would happen. Okay? However, all right, it's really, excuse me, it's the movement of solvent. That's what's going on with this thing. The semi-impermeable membrane allows solvent molecules to pass through, but not solute molecules. So, pardon me. So, however, if you have this situation now, though, where you have a diluted solution on one side, okay, solvent will pass through from the diluted solution to the concentrated solution until both now have the same concentration. All right? So as you can see, what happens here is water, so the solvent molecules will pass through to this side in an effort to make both of those solutions the same concentration. So it's diluting this concentrated side, and what you get now is this height of a water column. And recall from our discussion of gas laws, the difference in height of two liquids will create pressure. We call that pressure the osmotic pressure. Okay? Another picture of it can be observed here, where if, let's say, we have a beaker with pure solvent in it, and then this green stuff is a solution that's got this semi-impermeable membrane. Okay? Over time, the solvent will pass through the membrane. It will add liquid. Look, see how the liquid height in this volumetric flask is going up? Okay? And the difference in height of those two liquids, you know, from this height right here, the initial, to the final height, that creates osmotic pressure. Okay? Finally, another way to observe osmosis, or another way we can describe it, is back to the same U-tube picture right here. Okay? So yes, this is called a U-tube. This existed before YouTube, right? We're not talking about that. I'm talking about this. So again, another way we can kind of think of osmosis is if we have, once again, this U-tube with the membrane, and we have pure solvent on one side and a solution on the other side, we know that this pure solvent is going to want to migrate over to the solution. However, if we want to prevent that from happening, we can apply pressure to keep these liquids at the same level, and that pressure we have to apply is the osmotic pressure, which is given by the following equation. It's a very simple equation. So capital pi is the letter we use for the osmotic pressure. M is the good old-fashioned molarity. R is our gas constant, and 0.08206 liter atmosphere mole Kelvin, and then temperature is temperature in Kelvin. And so now it's important to notice if we have an aqueous solution with dissolved ions, we have to use the Van 't Hoff factor. If we did not have ions, and so, you know, if I back up just for a second here when we were talking about this, you know, suppose we're doing a covalent molecule, okay? Covalent molecules always have a Van Hoff factor of 1. So you dissolve the covalent molecule in the solution, it doesn't break up into any ions.